All right, so last time we started talking about the Perceptron Training Rule. That's where we're going to start. So this is the method. Hello. You guys are feeling honest, I'm glad. The Perceptron Training Rule is a method to update the weight going from neuron J to neuron I. It's based on the signal and then the error. This is the target minus the actual output of neuron I. And the idea here is that if there's no error here, then you can't really adjust the weight. And if there's no signal actually going along the path, then the weights are irrelevant to what the error actually is. So you can't blame that weight because it really didn't do anything. What we're going to do is apply this to a real simple network. We're going to train it to do the OR. So we're going to start with that OR problem. So I'm going to draw the network here, and then we're going to need a large part of the board to do the table for this. So here's our two inputs. So we have neuron 1, 2, and 3. W31 is 0.1. W32 is 0.1. This is typical with a neural net. You'll choose small initial weights. We'll talk more about that in a bit, but that's a good strategy to start out. And then we're going to calculate x1, x2, because that's just equal to inputs. That's easy. We'll calculate U3, then the input is 3. Calculate X3 is the output. Go on and have a seat. Get warm.
Good morning, Onon.
Get warm.
Yes.
Yeah.
Trying to.
Then we're going to calculate the output X3. And then we're going to apply the learning rule. So we're going to update the weights. And notice you have to have initial weights. You can move down here and do. You have to have initial weights to start out with because it doesn't calculate the weights in one shot. It just increases or updates them as you go along. And the other thing we need is we need a learning rate. And we're going to do a learning rate of 2.5. What I'm going to write on the board is exactly what I want you to do for the homework. You're doing it for the AND gate. We're doing it for the OR gate. You guys all know what the AND gate is? Somebody sent me an email. So for the OR gate, well, let me write out the training gate and then we'll see what the AND gate is. How it's doing. So the update rules, we're going to update W31 to W32. I'm going to write that up to the top here, and then we're going to do a table across. So the update rules for each of the weights, so W31, old and new, plus 0.25 times error, output 3, neuron 3, times x1. So that's the signal run along that path. We're updating this way. We do it based on the error at the output. Same thing for the other side. Notice we still did the error, but we have a different signal going along. So the only difference between this one and this is that this is X1 and this is X2, the signal going along that path. All right, so create a big giant table here. We'll have room here. We're going to have the input. That's good. We're going to locate or list the target. Okay. And then we're going to calculate U3. We're going to calculate X3. We're going to calculate this error. And then we're going to list X1 and X2 because we needed the update rules. We can actually just jump over here and grab them, but I'm going to list them here so we can see them better. And then we're going to update say W31, W32. Let's draw some lines down here. There. There. These will be pretty straightforward. So here is our set of data. The 0, 0 going in is going to give us a 0. The 0, 1 going in gives us a 1. The 1, 0 gives us a 1. The 1, 1 gives us a 1. So that's a 4 gate. Now for the AND gate that you guys are doing, it will be zeros. You have to have 1 and 2 in order to get an output. But for the OR gate, you just have this. The XOR gate, remember, then the 1, 1 was a 0. So that's a different gate. So we're going to OR gate. Oh, we need to list, remember what the threshold was here? Forgot that. Threshold for that is 0.5. These are linear neurons. All right, so let's calculate. 0, 0 goes in. So 0 here. 0 comes out because it's linear with a slope of 1. Because we could have a different slope, right? If we had a slope of 2, then you can multiply by 2. All right, so we can go ahead and copy those over here. So we get a 0 here and a 0 here. 0 times 0.1. 0 times 0.1, add them up, and we still get 0. So the net input is 0. And then we look at that and we say, well, that's less than the threshold. So that neuron does not fire. So the output is 0. Now we look, what did we want? We wanted a 0. We got a 0. So the error is 0. So the weight update rule says, okay, we take 0.1, which is the initial weight, plus 0.25 times a 0 error times a 0 x1 signal. So I'm using those formulas over there. So the weight does not change. because we got the right answer. Same thing here. For this weight, it's 0.1. Learning rate times the error is 0, the signal is 0, so the weight stays the same. So far, so good. On the 0, 1. The 0, 1 goes through. Let's list it here because we're going to need it in the weight update rule. So the 0 going through. So that's why x1 is 0. We have a 1 going through, so we get a 1 out. So that's why x2 is 1. So we have a 0 times 0.1, a 1 times 0.1. So the net input is 0.1, and it's less than the threshold. So we still get a 0 out. But now we wanted a 1, we got a 0, so the error is 1. So now let's update the weights. 0.1 plus 0.25. Now we have a 1 error. What's the signal along that path from 1 to 3? This value here, right? x1. So that's 0. So that way does not change. Why? Because the signal along this path is a 0, so it really doesn't matter what number we have here. We always get a 0 coming through that path. So we can't blame that weight for the error. How about this one? 0.1 plus the learning rate, error is 1. Now we have a signal of 1. So this weight does change. Let's go over to the diagram and change it. So that weight updated because this weight was responsible because of the signal for the error that was up here. Okay, let's go to the next one.
So Dr. Stack.
Yeah.
So after the W22 change, we're gonna use that number for next loop.
Yeah, that's why I wrote it on here. So now that weight is changed to this value, so we're going to use that from now on. Let's stick in the 1, 0. Got a 1 goes through, 0 goes through. Now we could have listed these more logically maybe over here in front of U3, but again I put them over there because we need them. So you can list them wherever you want. If you prefer to stick them over here, I'm okay with that in your home. All right, so 1 times 0.1 plus 0 times 0.35, we get 0.1. Less than the threshold, that's where we're applying the activation function. And so we get a 0 out. We wanted a 1. We have an error that's 1. Here's our signals. So we apply the same update rule. Error is 1, but now the signal on that left side is 1. So this weight changes. This weight's 0.35. We have an error of 1, but the signal on the right side was 0 right there. So that weight does not change. So we can go over here to our diagram now and write in 0.35. So you can see that as we progress through the data in our training set, we apply the update rules, and the weights hopefully are getting better and better. Okay, how about the last one? We have 1 and a 1. They get passed through, so this goes over here. We have a 1 times 0.35 plus a 1 times 0.35. 7. That beats the threshold. So that neuron now fires. This is the 1. What did we want? We wanted a 1. We got a 1, so 1 minus 1 is 0, so we have no error. So now look at what happens to the weights. Signal, oh, that's the error. Error is 0, the signal is 1. And now, because the error is 0, just like the first training period, nothing happens to the weights, because there's nothing wrong. Kind of the old adage of it ain't broke, don't fix it, right? The weights don't change.
In some ways, might this be a useful weight though, because like we have a condition where if we have a 1 on either input, but not both of them, we get a 0 out. Whereas like on other gates, like if it's 1 in either one, then you get an output basically that's greater than your threshold. So like unless both of them are firing, like both are 1, then you get your output. Whereas previously, where we only had 1, it would also fire, but in this case, if there's only 1, none of them fire. Like, is there a different type of logic for this way to be?
I mean, when you guys do the AND gate, it's going to be a different pattern here, because you're not wanting those middle ones to fire, but you want the last one to fire.
Yeah.
So you get different weights for that.
Well, I'm just saying with this one, we have a different weight, and I guess we haven't checked it yet after we've updated our weights.
Oh, yeah, and that's my next question is, are we done? We don't know yet, right? Because for 2 reasons. We got non-zero errors, so that means we were wrong some of the time. And we don't know if the weight updates fixed it or not. And then the other clue, so clue number 1 is there was some error. Clue number 2 is the weights changed. So both of those are indications that we need to keep going. So what happens is now we're going to do the whole thing again. And there's a name for this. This is called an epoch. One pass through the training set. This is called an epoch. An epoch is like a long period of time. It might be like 1,000 years. It's a long time, right? So they just chose that. I guess we could have called this a century or a decade. But so we're not done. We're going to do it again. So there's our next set. We can do this faster because we're good now, right? 0, 0 goes in, 0, 0 comes out, times the weights, we get a 0 net input. Less than the threshold. Neuron does not fire. We wanted a 0, so the error is 0. So with 0 error, the weights don't change. That's good, right? How about now? Let's go this one, 0, 1. 0 times 0.35, 1 times 0.35. Net input is 0.35. Less than the threshold. No firing. Give an error of 1. Signal was a 0 and 1. So this update this way. Got an error of 1. The signal was a 0. 0.6, right? So now let's change this way. Thanks. Okay, let's jump down to the next training pair, 1, 0. 1 times 0.35, 0 times 0.6. No firing, 0 output. Error is 1. That way, that takes. This one does not because the signal is 0. So now let's put in the 1, 1. 1 times 0.6, 1 times 0.6, we get 1.2. Threshold beaten. This neuron fires from 1 to 1. Error is 0. No error means that the weights don't change. So we just did another epoch. Are we done? We don't know yet. Because we still have some error and the weights changed. So we need to do it again.
Yeah, I was gonna say my question from earlier, basically, it's already happened. My question, easier to narrow down, is if our targets were actually 0, 0, 0, and then 1, is there a different type of name for that type of, is that like, would that be a different type of gate?
That's the AND gate.
That's the AND gate.
You're saying 0, 0, 0, 1, right?
Yeah.
Yeah, that's the AND gate. That's what you're doing for the homework.
Okay.
Sorry, I didn't follow what you were actually asking. So we have to do it one more time. So I'm going to jump back up here and use this part of the table again. The inputs are going to be the same, right? All right, so here's our weights, 0.6, 0.6, put in the 0, 0 times 0.6, 0 times 0.6. 0 comes out, net input, 0 is the value because it's less than the threshold. We have 0 error. So the weights don't change because there's no error. Okay? 0 times 1. So 0 times 0.6, 1 times 0.6, 0.6. Here, our net input is 0.6. We beat the threshold, so we fire. The error is 0. The weights don't change. So far, so good? Because we're experts at this now, right? Okay, now 1 goes in times 0.6, 0 times 0.6. We get 0.6 is the sum. Neuron fires. We wanted it to fire, so the error is 0. The weights don't change. Now we got the 1, 1 going in, 1 times 0.6, 1 times 0.6. 1.2 beats the threshold, neuron fires. We wanted a 1, so we get 0 error. And the weights don't change. Are we done? Sure looks like, because if we did it again, nothing's going to happen, right? So the one clue is we have 0 error over entire training set. So that's the ultimate goal. We want 0 error because that means it's giving us the right answers. Then the other clue is the weights don't change. So in the homework, when I say does it work or does it not work, that's your clue. If you're getting 0 error, it works. If the weights aren't changing, it works. If either one of those is not happening, if you don't get 0 error, or the weights keep changing all the time, then you're not done. It's not working. Yeah.
What if we got like 0 error, but the weight change?
You can't.
Oh yeah.
Right, because all of the weight of the rules, if you have 0 error, the weights don't change.
Yeah.
So nomenclature, the input paired with the target is called a training pair for that reason. So the training set is comprised of training pairs. So the input paired with target. Paired, so let's fix that up. This is called a training pair. This is called the epoch. Already said that. This is called the input layer. This is called the output layer. I think we already said that. So let's say that we had, instead of 0.6 for a weight here, we have 0.7. Would this still work? Yes. Would, right? What if we change the threshold to 0.6? Would still work. So again, like we talked about last time, there's no unique network that will do the job. There's a lot of different networks that will do the job, and what we're going to do is find one that works. All right, so let's apply the perceptron rule to the XOR. Remember, for the XOR, we have to add that hidden neuron. So let's draw the network and see what happens. Any questions about this, about what you're going to be doing on the homework? You'll have, well, you have 3 different ones you did, so there's 3 different pages you'll have with this table on them.
Is there a particular reason you draw the network from bottom to top?
Just the way that I do it.
Okay.
I guess if you could draw it top to bottom, you think about it as information flowing down. You could draw it sideways if you want. I don't know. But that's the way I always see it in books, and it's the way I can draw it.
So basically, if we increase our learning rate too much, what happens is it just keeps going up and it's never able to go back down in terms of the new weights. That way you know confused because it can't ever, but learning rate is set too high, it will never come up with the right answer.
Yeah, because if we used a really big learning rate here, this one probably would work, right? You would just automatically just jump to a big weight value and then all three would work. But there's other problems where if you have too large a learning rate, you have problems. Almost like something happened to this word. It's the same stuff we've been using forever. I need to erase that too. So we're going to look at the XOR now. Let's train this network. What is it? 4, 3, 1. Chooses a W4 1. 4 2. W4 3. By the way, the point 1 is not magic or necessarily required. And in fact, later on we'll talk about how actually choosing random weights is better than making them all the same. But for these examples, it's easier. So this is called the input layer. As the inputs come in, this is called the output layer, just like before. Because the output of the network is going to be X4. And this is called the hidden layer. I think I mentioned that last time. Because it's hidden from the input and the output. All right, so let's write the learning rule for each one of these. So we got W, I, J, U, here's the error, here's the signal. So let's write, let's do W41. So that's T4 minus X4 times X1. So X1 is the signal coming out of here. X2 is here. X3 is here. X4 is there. T42. And we'll do 4-3. So far, so good. I'm just using the I's and J's matching the numbers, right? And notice I started with the way it's going to the output. That's typical. Kind of makes sense because we have an error that we know up here, so you start that way. Now let's go down to the W31. Right, so X1 is the signal along the path from 1 to 3. The target and the output are for neuron 3. So there's our formulas. So if we start to calculate this, we'll put in like a 0, 0, and our target for the XOR is a 0. So we'll calculate, this is X1, this is X2, so we'll calculate U3 and X3. They're all going to be zeros, so I'm just going to list what we need to calculate. And then once we calculate X3, then we can calculate U4 and X4, right? Because we know all the information that goes into that. We know X1, X2, we know X3, so then we can calculate U4 and X4. Now we have a target here, so we can calculate E4. We're going to need that. This is E4. All of these are right here. E4, right? So we're going to need that. In fact, what's that going to be? We got zeros everywhere. We're going to have 0 error, right? So we can stick that in. It's going to tell us not to update this or this or this, so we're good there. How about E3? We calculate that. We got X3. What's T3? This is T4.
It's T3 the same T4.
What we're really saying is, what do we want coming out of 3 that's going to give us the right answer? We don't even really have a right answer for 3, do we? So we don't know a target. So we can't calculate E3. Because we don't know T3. So we're stuck. We can't do these. So if we're told to do the Perceptron Training Rule, and we have this neuron in the middle that is not exposed to the output, in other words, it's a hidden neuron, we're stuck and we just go home because we can't do it. In fact, this was a major issue when they were developing neural networks in the 50s and the 60s, is they were doing that perceptron, trying to do images recognition. And they realized that to do anything complicated like an XOR, which is a nonlinear gate, you can't do a perceptron training rule for anything that requires a hidden neuron. And a lot of interesting problems required a hidden neuron. The mathematicians actually proved that you couldn't map a lot of different functions with only an input neuron layer and an output neuron layer. And so everybody that was working on neural nets said, well, this is a bust. All we can do is these real simple functions that are linear. We can't even do an XOR gate, so they quit working. Because it was a dead end. They couldn't train. So the Perceptron Training Rule only works for what's called a 2-layer network, an input layer and an output layer. Sometimes that's even just called a 1-layer network. And people stopped working on neural nets. They said this is a waste of time because we can't do anything even as complicated as a simple XOR network. And finally, in the 50s, in the 80s, in the late 80s, somebody figured out how to train a hidden neuron, and then the whole thing exploded again because they found out a way to learn. So that's what I'm going to show you next. It's called error backpropagation. And it's a method to get the error that we know at the output layer back to this hidden neuron so that we can train it as well. So we'll spend a couple of days talking about that. And that's what most people use now to train, is some form of error backpropagation for training. Deep networks, which you hear about maybe, the stuff that like Siri uses for voice recognition, the Postal Service uses for handwritten recognition, all of the text to, the handwritten digits to character recognition. Almost all of that stuff uses what's called deep networks, where they have maybe 10 or 15 layers of these hidden neurons that do pattern and feature recognition. And they assign different neurons in there to recognize different features, and that's how it picks up your speech and categorizes it into words and what it's supposed to understand. A comment, even with this simple OR XOR network that we did, it's starting to get pretty complicated, didn't it, to do it by hand? So most of the stuff that we do is the software is written to do these calculations for us. Because once you experience this, you know how it works, and you'll understand it. And then we'll just use software to do the calculation. So this is in chapter 4 in DEHA. And I've given you copies of that on Blackboard. So let's read that. And it's also in chapter 6 in your textbook. So we'll start reading that. This is called back error propagation. So most people call it backprop. And I'll show you the most simplest form. The software that we use has a whole bunch of bells and whistles added to it that improve it. It still works with the same basic idea as the Perceptron Learning Rule, is if the weights are wrong, change the weights in a direction that makes it better. That's what the Perceptron Training Rule is. So it's to reduce the error. This is used on feedforward networks. Which is what all of the ones I've been showing you. Notice that the information flows from the inputs to the outputs, and there's no feedback. There's no recurrence. So feed forward, there's no feedback connections. The problem with the feedback connection is if you have a feedback from, say, the output neuron back to one of the other neurons, you need to know the output of the output neuron to calculate the output of one of the middle neurons, but you don't know the middle neuron, so you can't calculate the output neuron. You follow? Because you need like X5 to calculate X3, but you don't know X3 to calculate X5, so you can't get X5 to calculate X3. We'll talk about those later. So these are feedforward networks. Backprop works on these. Here's a kind of generic structure we're going to use. It will look real familiar because it looks like what we've already been doing. We'll say there's n input neurons, so there's an input layer, I1, I2, out to I sub n. There's one or more hidden layers. So I'm just drawing one, but you could have more. And then there's an output layer with M neurons. Where is it there? And all of these networks can be connected forward, going up. Typically, we just connect them layer to layer, like this, where this entire input layer has connections going up to the next layer. And then this has connections going up here, like that. But there's nothing to preclude connections going from this layer and jumping up to that as well. And the software will have an option to do those connections if you want. From each of these, we'll collect an output. So there'll be M outputs. And then almost always we'll put in what's called a bias neuron. And it'll be called number 0. And it always outputs a 1. And it will typically be connected to every neuron in the network. And I'll tell you more later about why we do that. So the inputs go through up to the network. The bias is neuron number 0, always outputs a 1. And the network learns with training paired data like we've been talking about. So you'll have inputs paired with target outputs. So we have a training set. We have inputs I1, I2, I sub n, and we pair them with targets T1, T2, all the way to T sub n. We have a whole bunch of those pairs. And the process is very similar to what we just did. You apply an input here. You do the forward propagation and calculate the outputs. So step 1 is apply input vector. Notice we can think of this as a vector like n. Calculate the output vector, and this is what's called the forward propagation. We do that for each training curve, just like we did with the perceptron. Step 2, calculate errors. This is an error vector for all output neurons. And notice now we've expanded this to more than one output neuron. With the perceptron, the XOR data was just one output because that's what we were doing. But you can have more than one output. And you can calculate an error for each output. It's just O minus T. So that's the error calculation, and then step 3, you backpropagate errors backward through the network. And I'll give you the formulas for that. We're not going to do that exactly right now. I think we'll probably do that next time. So you backpropagate, so then you're going to get an error that you're going to assign to each of these hidden neurons, and that's how we can update the weights, which is step 4. So we backpropagate the errors, and we update the weights. And then you repeat, just like we did the Perceptron. In fact, the weight update rule is going to look a lot like the Perceptron Training Rule. It's just how we get those errors for those hidden neurons. You guys have a hard time seeing it. You can say something, or you can just stand up and make it obvious. And then you go back and do it again with the next input, and you just keep going. The people that get credit for making this thing happen, which made neural nets actually work, were a guy named Paul Wirbos, who was doing economic models in the 1970s. And nobody connected what he was doing with neural network architecture of the perceptrons in the 50s. But it turned out when people actually invented it for networks, they look back and go, oh, this guy did it in the 70s. And a guy named David Parker essentially reinvented it. And still, it wasn't a big deal. He just reinvented it. But then, often with inventions, you need somebody that publicizes it. And then these guys wrote a textbook about machine learning and artificial intelligence, where they said, hey, look, we can use this thing that this guy did and this thing that this guy did and do cool stuff. And that's when it really took off. I'm going to set this back up because I'm going to put something up. I'm going to share the screen here.
Just curious for like midterm stuff, are names important?
These what?
I like those names important, like to know, like for
Yeah,
or something.
I want you to know who invented it, yeah. This guy ended up being a director at the National Science Foundation and was a huge promoter of artificial intelligence and funding to the National Science Foundation. And then there's a guy along the way, a guy named Yan LeCun, who did a lot of neural net stuff, but his big deal was he created deep networks and deep learning, a way to structure networks and train really deep networks that could do all of this pattern recognition, image processing, language processing. All right, so instead of spending the rest of today talking about more details of backprop, I want to show you some fun examples of this. I'm going to have to share my screen so Zoom people can see it. That's not what I wanted. There we go. Oh, those are screens, okay. Are you guys seeing that up there? No, you're seeing the other screen. There we go. So this is the one you need to look at over here. So while I was learning about neural nets, I was taking a class required for the PhD where you had to learn a foreign language and then translate 40 pages of text in that foreign language into English. It's a pretty daunting task. Fortunately, I took 4 years of French in high school, so I knew French already. Now, the 4 people that hadn't learned the foreign language were struggling, but they still took the class. And so it was a semester-long class where you learned the language well enough to translate the scientific text into English. So I was taking a class in French, and I was learning neural nets, and I thought, well, it'd be really cool if we could make a neural net translate French words into English, so I didn't have to do all the hard work, right? So I did that with just 2 French words. One's bonjour. Anybody here speak French? It means hello. You guys probably knew that. And then beaucoup means a lot or much. So my idea was to create a network where you'd send in letters in French into the input layer and then get English words out the top. The reason I show you this is, I mean, it was successful with 2 words, but there's a lot more to language translation than just word by word translation. And Google actually does a pretty good job with it now. You can go to Google Translate. And there's a huge artificial intelligence engine behind it, where not only does it translate words, but it actually can translate sentences and do idiomatic expressions and all that. But that brings up, the reason I show you this is how am I going to put in a letter into a neural net when the neural net processes numbers? So that's one of the key issues we'll look at throughout the semester, is that you've got to encode your input data properly to get it into the network. We'll look at cases where, in fact, one of the things I'll show you today is trying to sell condos to people and they put in their zip code. Well, that's a number, but then how do you use that zip code to actually get it into the network in the proper way? So a natural way is just to assign numbers to letters, right? Like an A is worth 0.05 and a B is worth 0.1 and so on. So you can do that, and that allows you to get the letter, the word bonjour, into the network. But then there's something implied in that, right? It means that an A and B numerically are close to each other, but in words that may not make sense, you know, the language translation. But that's what I did. So I assigned numbers to the letters. Those became the inputs. The network calculated numeric outputs, and then they got interpreted back to letters in English. So that brings up a key feature is you've got to encode the information properly to get the neural net to work. So this is a printout of my little simple program to do a neural net to learn, to take bonjour in and go hello out. And I started with really small weights, and small numbers were mapped to the blank, to the character blank. And so bonjour went in, got multiplied by really small numbers, and the output is what's underneath bonjour there. So what came out was blank, 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 blank. It wasn't cursing, it was just blank. And the correct answer is hello, so that's what's over there to the right. So bonjour goes in, the network calculates, gives blanks because the weights are all small. The training program says, nope, wanted hello. It updates the weights. Beaucoup goes in, and notice now, it actually gives something out. It says And the program says, nope, wanted much, update the weight, Bonjour goes in, we get commit to go, correct answer is hello. This repeats over and over again. It's like training a little kid, right? Keep doing this. Many presentations of just those two training sets. Over here, after going all the way down this column and then going through here, we got bonjour, we get dixtal, starting to sound a little bit like a word. Nope, we wanted hello, beaucoup, brokefoot. Nope, we wanted much. It's learning, but it's slow. Keep going. Notice here it's getting closer. Here, beaucoup, it gets mechta. Bonjour gets holds. Getting closer. Mochva. Here it's got hildi and much. Oh, it got one right now. So it's getting better and better. And then as you go down, you can see bonjour gives hello and beaucoup gives much, and it's getting the right answer. Well, this illustrates how you have to encode the inputs, and it also shows you how it slowly learns. It's slowly updating the weights to get the correct answer. People have done a lot of stuff with neural nets, so I'm just going to show you a few quick examples. The natural thing is to, well, let's predict the stock market and make a ton of money, right? So these guys were doing that with the Tokyo Stock Exchange. And again, here you have to say, well, what are the inputs that you want to put into your network that are relevant to figuring out whether you should buy or sell stocks? And in fact, that's all they're really doing is they're creating a network that looks at financial data and tries to predict whether you should just sell or buy. They're not saying buy this stock or sell this stock, just should you be putting money into the market or should you be selling? And so they trained it on a bunch of historical data, and then they took some other historical data that came after that and tried to compare their prediction system to with just buying and holding stock. And they were able to beat with their prediction system the buy and hold. There's a lot more of this being done now. This was early on. In fact, my neighbor, who's a pathologist, his son has a PhD in physics. Guess what his job is? He lives in Manhattan. He works for Wall Street, and what he does is he does numerical models trying to model the stock market so they can decide whether they're buying or selling. There's dangers in that because if you let computers start buying and selling and telling you what to do, then weird things can happen. There was 20 years ago, the stock market went crazy. They shut it off, and they found out that some of the computer algorithms had picked up on a glitch, some weird thing in the data, and were telling everybody to sell. And so the prices went way down, and everybody's sitting there going, what's going on? Because nobody was making the decisions. They were just trusting the computers. This guy did some AI programming. In fact, he created a mutual fund called the Neural Fair Value that picked stocks based on neural nets. And that was something you could actually invest in a while back. So that's more stock market prediction. There's another method called genetic algorithms that mimics evolution that helps learn how to do stuff. See what else I got? Yeah. So this article, I don't think I have this posted yet, but I'll post these online. This is Robo Trading 101. There was a guy named William Peter Hamilton who was a great stock picker. He died in 1997. Oh no, he died in 1929, but people were using an artificial intelligence algorithm trained on his strategies to pick stocks based on the human brain. Here's another fun application, predicting the box office success of motion pictures with neural nets. These guys said, hey, let's look at the PG-13 rating, send that in, look at what other movies in production are going to compete with it, what's the star value? Does it star somebody really popular where people will go see the movie no matter whether it's good or bad? First thing you have to pay them more, right? Is it a comedy? Is it action? Is it sci-fi? Does it have cool technical effects? Is it a sequel? How many screens is it going to be released in? And they were trying to predict whether it's a flop or a blockbuster. And so they did some training on that. Here's another case where they were looking at images from Doppler radar and trying to predict whether there's a tornado in the Doppler radar signature. So they were looking at all these measures of the radar, sending it into a network and trying to predict whether a tornado was there or not. So there's lots of cool stuff you can do with neural nets. And here in a bit, I'm going to make you an assignment where you're going to look for, and you can start looking now, look for a cool application of neural networks that you're interested in. And I'll have you guys do a one-page write-up, and then you'll do a real quick presentation to the class about what that is. And there's no good or bad examples, but a good one is one that's fun for everybody in the class and that you're excited about. So I'll make that assignment. I've had people look at predicting outcomes of football games or soccer games. One was a paper on a program trained with neural nets to do online soccer, like video game soccer. There's been all kinds of stuff. So start looking for something cool that you're interested in. You know, if you have a hobby, look for papers in that. You just do a Google search on artificial intelligence, neural nets, and whatever your hobby is. All right, so I did all those. Next time, we're going to look at the details of backpropagation. So we'll get into that next time. You guys are working on a homework problem, a homework set for next time. When you're doing that, I've asked you to scan it in as a PDF, right? And upload it to Blackboard. All right, stay warm.